So in this class today we will discuss about the distance or impedance relay for the transmission line. Basically this type of relay are classified at definite distance relay and second is the time distance relay. So we will discuss one by one what is definite distance relay and what is time distance relay for the production of transmission line. First we will discuss the definite distance relay. So before discussing this definite distance relay, let us go to the circuit diagram. So this is the circuit diagram. This is the restraining coil which is operated by the voltage, and this is the operating coil which will be operating by the current. This is a beam and this is a hinge. So this beam is normally balanced on this hinge and these are the normally open contacts. So in normal condition this restraining coil will have a more operating torque compared to the operating coil. So what will happen that this force will be more downwards compared to the operating coil. So this beam will tilt downwards. Hence once beam will tilt downwards in restraining side, so what will happen, these contacts will remain open. These contacts will remain open. Now as soon as there is a fault created in the circuit, so what will happen, the current will increase and voltage will go down. Voltage will go down. So ratio of V by I in that condition will be less, and this value will be within the protected zone area. So as in previous classes we have discussed how the distance production operate. Distance production operate that once the impedance of the relay which is set is less than the set value, then the relay operates, and if the impedance measured by the relay is more than the set value, then relay will not operate. It means fault is outside the zone. So here also this is the restraining coil which is operating by the voltage. It means voltage is applied to the restraining coil and this current is applied to the operating coil. Both coils will develop the torque, but in normal condition the restraining torque will be more than the operating torque. So this beam will be pulled down this side compared to the operating coil side. So this portion will go up. It means these contacts will remain in open position. And as I have discussed that whenever there is a fault in the system, then due to the fault current will increase sharply and voltage will go down. It means ratio of voltage to current, that is the impedance, will be less than the set value. So the relay will operate as a distance production. Now let us go what description has been written in this for this relay, that is called the definite distance relay. So this is simply a variety of balanced beam relay. Here one beam is placed horizontally and supported by a hinge on the middle. Already I have discussed the same thing. And one end of the beam is pulled downwards by the magnetic force of the voltage coil fed from the potential transformer. Always voltage coil is fed from the potential transformer and operating coil is fed from the current transformer. So other end of the beam is pulled down by the magnetic force of current coil fed from the current transformer connected in series with the line. Now due to the torque produced by these two downward forces, the beam is staged at an equilibrium position And the torque due to the voltage coil serves as a restraining torque, and torque due to the current coil serves as a deflecting torque. So under normal operating condition, the restraining torque is greater than the deflecting torque. Hence, the contacts of this distance relay will remain open. Now when any fault occurs in the feeder, so under protected zone, voltage of the feeder decreases and at the same time current increases. So the ratio of voltage to current, that is the impedance, falls below the predetermined value, and in this situation the current coil puts the beam more strongly than the voltage coil. Hence beam tilts to the close the relay contacts, and consequently the circuit breaker associated with this impedance relay will trip. So this is what about the total the operation of the distance relay production, definite distance relay production. And for this description, the circuit diagram is shown here in this slide. So this circuit already I have discussed that how the distance relay will operate if there is a fault in the transmission line. I think this is clear. This is a very simple system, so it must be clear to you. Now we'll move upon the second relay, that is called the time distance impedance relay. So let us first discuss that what is the structure of this time distance impedance relay. Let us first see, this is the spindle which rotates in the clockwise direction, and there is some voltage restraining magnet. This is a hinge magnet coil, and this coil is mounted over this magnet. So this is called the voltage restraining magnet, and these two contacts are going to the trip circuit. Now further this link is wounded with spiral spring coupling. Here there is a spiral spring coupling, and whole this is connected in series up to here. Now downwards we see again one magnet, and the coil is wound on this magnet. This is called the current coil, where current is supplied to this coil from CTs. This relay is nothing but it is also called the induction type overcurrent relay. This is called the induction type overcurrent relay. So what will happen in this case also, that voltage is applied to this restraining coil, and current is applied to this induction coil. So in normal operating condition, here also the restraining torque developed by this voltage coil will be more than the torque developed by this current coil or operating coil, or we can say this is the induction overcurrent relay. So in that condition, what will happen, that this spindle moves away from the contacts, and these contacts will remain open against this spiral spring force. Now a condition will come when there is a fault in a transmission line. So once there is a fault in transmission line, then the current will increase towards the fault, and this current will increase in this induction current coil also. So as soon as this current coil in a current increases in this induction current coil, the operating torque is exceeding from minimum value to the maximum value. So what will happen? This spindle is attached to this spiral spring coupling. So this starts rotating, and against the spring force, that is the spiral spring coupling. And this disc will carry on rotating until this spring force is sufficient to pull down this contacts in the closed position, or we can say that the torque of these CTs developed will try to rotate this spindle against the spiral spring wire coupling, and it will carry on rotating up to a certain angle until unless this torque becomes greater than the voltage coil torque. So once this torque will become greater than the voltage coil torque, then spindle will carry on rotating to the maximum angle against the spiral spring coupling, and this contact will become closed. So the commands will be extended to the circuit breaker to trip the circuit breaker, so that faulty element will be eliminated from the transmission line. So this is what about the overall structure of the time distance impedance relay. And here we can say that operating time is proportional to the voltage applied across the potential transformer. It means if more voltage applied across the potential transformer, so operating time will be less because the disc will move more faster. And similarly, here this current is applied to the current transformer, and this current will increase if there is a fault. So if there is a more current in this coil, the disc will rotate more faster and contacts will close in a very less time. It means this operating torque or operating time will be inversely proportional to the operating current. However, here this operating time is proportional to the voltage. So this is what the structure of the time distance impedance relay. Now we'll discuss the description as given in the next slide. So during normal operating condition, the attraction force of armature fed from PT potential transformer is more than the force generated by the induction element. Hence, relay contacts remain in open position. Now when a short circuit fault occurs in the transmission line, the current in the induction element increases, then the induction element starts rotating. The speed of rotation of induction elements depends upon the level of the fault, that is, quantity of current in the induction element. Now as the rotation of disc proceeds, the spiral spring coupling is wound up till the tension of the spring is sufficient to pull the armature away from the pole face of the voltage excited magnet. So this is what we have discussed by seeing that circuit diagram. Now the angle through which disc travels, the disc travels before the relay operates, depends upon the pull of the voltage excited magnet. So this has been told earlier also that disc travel will be proportional to the voltage applied across the voltage coil. Now greater is the pull, greater will be the travel of the disc. So the pull of this magnet depends upon the line voltage. It means if greater voltage is applied across the voltage coil, then the torque will be developed more and disc will move faster. Now the greater the line voltage, greater the pull, hence longer will be the travel of the disc. That is, operating time is proportional to the applied voltage across the voltage coil. Similarly, if we talk about the current, then speed of the rotation of induction element approximately proportional to the current in this element. Hence, the time of operation is inversely proportional to the current. So here it is shown that operating time is inversely proportional to the current, and if we talk about the voltage element, where the operating time is proportional to the voltage applied across the coil. So this is what about the distance, time distance impedance relay and definite distance relay operation for production of transmission lines.